Okay, so let's just talk a little bit about standing waves, mostly because I can't think of a problem for them, but I'm sure there are some. So a standing wave could be, for example, if you tied a string on both ends, like a guitar string. Tie it here, like that, right? And the unstretched length here is, we're going to call this L. So this whole length will just be L from side to side. And something that you can do is kind of pull down on it and it'll go boing. So if you've done anything like this before, you know it can do this. So I guess I'll make one of them solid and sort of, bounce up and down real quick between those two positions. But if you pull harder or something, it can do something more like this, where it forms these two sort of football shapes. And you can actually get it to form any number of football shapes. Let's see if I can get them. They should be the same length. I'm trying my best. Okay. There, like that. And so these are called standing waves. You can see a wave, or like 1.5 waves, or whatever, but it's not exactly moving along, it's just moving up and down. But some waves do that, so they're called standing waves. And we can analyze this situation pretty well. For example, I said that the distance from the two sides is L, right? Well, look at this one here with the two bumps. I've got one wavelength visible, right? Remember, a wavelength is to go up and down and back up to where you started again. So this is one wavelength here in my picture with two bumps. So I know that in the picture here, the wavelength is L, right? Now in this picture above it, well, that's only half of a wavelength. So in this picture, half of the wavelength is L, right? Now down here I've got 1.5 wavelengths, and it's a little hard to get used to it, but this is one wave right here. And then this is half of a wave afterwards. So here I've got 1.5 wavelengths. So 1.5, I'll say, instead of writing 1.5, I'll write 3/2 of a wavelength. 3/2 wavelengths is L. Like that, and we can go on like this. But a pattern emerges eventually if you call this let's make something up here. I'm gonna say that there is one thing here, two things here, three things here, and you can see what I mean, like half wavelengths or bumps, essentially. One bump, two bump, three bumps. Well, you can actually end up making an equation that will give you any of these wave relationships between wavelength and L. And it's that, let's see, how do I do it? Wavelength, so N over 2 times wavelength equals L. Right, if I note, so I use this equation, plug an N of 1 into it, and I would get 1/2 of a wavelength equals L. If I plug an N of 2 into it, I get 2/2, or 1 wavelength equals L. If I plug an N of 3 into it, I get 3/2 of a wavelength equal L. So I made a general equation here for N is equal to any whole number, whole positive number, like that. And you can have any number of these standing waves. Alright, now that can be rearranged for wavelength, which I think it usually is. Wavelength is equal to 2L over N. And then recalling a rule of all waves, that the velocity of a wave is equal to its frequency times its wavelength, I can actually solve for the frequency of standing waves instead, which is, I think, used more often. So let's see, frequency is equal to velocity divided by wavelength, right? Wavelength is 2L over N, so what I end up getting is that frequency is equal to velocity, I'm going to write it NV over 2L. So I've just plugged my wavelength here into my frequency equation here to get this frequency of n, we'll say, is equal to whichever n you pick, some whole number, some whatever number you want there, times the velocity of the wave divided by 2 times this length. Okay, so there we have it. We can find the different frequencies that a string can vibrate at, or that any standing wave can be at, and I'm using a string as an example, right? And it's a good example because, well, that's why guitars and stringed instruments have particular sounds. Depending on the string you use, a string can only create certain frequencies, these frequencies, and they have names. So if I plug in an n of 1, that's called the fundamental frequency. So I would put in a 1 here, where n is. But of course that's unnecessary, right, to multiply by 1. So this is called the fundamental frequency when you plug in a 1 for n, and it's also called the first harmonic, if you're interested. And this would be the second harmonic, the third harmonic, and so on. And you can only have these frequencies. Well, think about it. If you look at the picture here, I have to have a whole number of n, right? I mean, just logically, I couldn't have, if it's supposed to be tied off at both ends, well then how could I have like that, right? It has to be tied at that end, so I can't have, 1 1/4 wavelengths happen like I was trying to draw here. It wouldn't work because it doesn't tie to the other end. So just from what we reasoned earlier, we have to have these whole number n's, which means, you can only have these discrete frequencies here. So that's just a little bit about standing waves in general. In the end, this really is the important equation about them. Oh, and just one more thing, sir. These are called nodes. This spot, 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 this spot. See in the pattern? Wherever they cross along, they make a line there, the horizontal area. Those are nodes. Nodes. And these, what should I put, a star? These are antinodes. Antinodes. Just a bit of vocab for you. Don't ask me. I just work here.